Are you trying to learn how to differentiate exponential functions, but every time you do your homework, you keep getting things wrong? Well, after you watch this video, you're not going to be having that issue anymore. I'm going to be going through every single example that you need to know to be able to tackle even the hardest exponential questions. Hello and welcome. I'm Jessie. These are my study notes. I break down math in a way that actually makes sense, and I also give study and productivity tips to help you navigate high school maths. If you like what you see and you're ready to enter your study era, hit that subscribe button and let's get to it. First of all, when we talk about the derivative of an exponential function, let's have a really good idea about what an exponential function is. Now, to put it simply, it's essentially any equation or any function in which the base of the power is a number, is a constant, and then the power is something in terms of x. So 2 to the power of x, 5 to the power of x. Later on, we're going to be looking at e to the power of x, where e is something called Euler's number. Now this here is this irrational, infinitely long value that's equal to approximately 2.71828 ... This can be found on your calculator. He's kind of like buddies with pi, where pi is also an irrational value which has an infinite number of decimal places. So whenever you see Euler's number, just think about it's just like pi, because pi is easier to grasp because it's something that we've dealt with from year 7 and 8. All right, now what I'm going to show you over here, before I really show you all the different formulas, just to have an idea of why Euler's number is so powerful, is if I look at this diagram, this displays the exponential function 2 to the x, so it looks like this. It looks like this graph where it starts off slow, then it grows exponentially. That's why we call it an exponential function. And then I've drawn on top of it its derivative. Okay, now I'm not going to tell you what the derivative is, just accept that this orange graph is the graph of the derivative of 2 to the x. Okay, we're going to learn later what that is. You can see here that it looks very similar to the exponential, but it's like a little bit slower. Now, if I look at this diagram over here, I have drawn y is equal to e to the power of x. Remember where e is Euler's number, this infinitely long, very random set of decimals. And on top of it, it is actually drawn the derivative. And what you will notice that is so interesting, and it only works when the base of the exponential is e Euler's number, is that the original function and its derivative is exactly the same. Whoa, what? It's crazy, right? No other function in maths exhibits this property. So that means that if I have y is equal e to the x and the question asks you to differentiate it, you will get e to the x. And if you differentiate again, you get e to the x. And then again, e to the x, you get the idea. Very, very cool. Okay, if no other number exhibits this property. So now when I explain to you the different formulas that we deal with in differentiating exponential functions, we're going to actually be breaking it down into two types. We have where the base is Euler's number, and then where the base is not Euler's number. Okay, and I'm going to tell you right now, it's crazy, it blows my mind, but you can get assessed on all 4 of these formulas, but only 3 of them are actually in the textbook. Yes, because this one here is actually on the reference sheet, in the New South Wales NESA reference sheet. But if you have never been, if you're not familiar with utilizing it, then when you see it in the reference sheet, you're going to be very confused on how to apply it. And I'm going to help you figure out how to do that. All right, so first things first is we're going to look at the first formula where the base is e, because these are the most common type. Now, if you have y is equal e to the x, when you differentiate it, you get e to the x, just like what I explained before. Now, if you have, for example, 2e to the x, okay, this is no surprise here. If you differentiate it, the constant 2 carries over. Any constant at the front, I call it a spectator, just comes along for the ride, and then you just need to differentiate the exponential function. That just gives you e to the x. So that's the same thing, perfect. Now, the more common formula that you will use and you will see is this one here, e to the power of f of x. So this is whenever you have a type of function where the base is e, but the power is something more complex. So it might look something like e to the x squared, it might be e to the 5x plus 2. These are all just different examples. And in this case, f of x would be x squared, or f of x could be 5x plus 2. Now, the way that you think about this formula is you want to take the power and then you want to differentiate that power. And then that comes to the front. So that's f dash x. And then quite literally, you copy and paste whatever you had before, and that becomes part of your derivative. Everything copy and paste. The power stays the same. That is the most important thing about exponentials. You don't bring the power down, reduce it by 1. No, you leave it the same. So for example, if I had e to the 5x plus 3, what you're going to do is you're going to take the derivative of the power that comes to the front, and then you literally copy and paste. Great. Let's look at the next one. So these next two are for when the base is not e. I cannot tell you how many times I've had students always forget this. I can teach it to them 5, 6, 7 times throughout the year, but because it honestly doesn't appear that often, but it has appeared many, many times in HC, but it doesn't really appear that often like in the textbook, or it doesn't really appear that often when you're doing classwork. You kind of forget about it. Students tend to forget about it, and then they rush to look at the reference sheet to see what the rule is. But I'll tell you now, if you have a base that's not e, we generalize it by calling it a. So it could be 2 to the x, 3 to the x, 10 to the x. Then its derivative is going to be, well, first you copy and paste, just like what we've been doing before. But the extra thing you have to do is you need to take the natural log or the ln of the base. So for example, if you had 2 to the power of x, you copy and paste, and then you take ln of the base, which is ln of 2. Wonderful. Now, I'm about to show you the formula that is not in the textbook. Very naughty, but you still need to know how to use it. It is if you have a to the power of f of x. So now you have base is not e, but you also have a power that is more complex. What you have to do is you take the derivative of the power, bring it to the front, that's f dash x. You copy and paste just like we have done before, and then you take the ln of the base. I like to think of this fourth formula as being a combination of the previous where the base is not a, but also of this one here where the power is not just x, it's something more complex. Okay, merge those two together, boom, that's your fourth formula. So I'll show you an example. If we had 4 to the power of 3x, the first step here is you take the derivative of the power. So the derivative of 3x is going to be 3. You copy and paste, and then you take the ln of the base. That's it. Beautiful. The hard thing though is just committing that to memory, but keep doing it, keep doing it, keep doing it, and then you got it. Okay, now the only thing I did in this last step is I combined the constants together. Remember that when you take the natural log of a number, so ln of 4, ln of 2, they're just numbers. Students seem to not be able to like wrap their head around the fact that this is just a number. But if I put in the calculator, ln of 4, it's going to give me 1.38629, blah, 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 blah. Okay, so it's still just a number at the end of the day. Okay. Perfect. We are now ready to tackle the questions. Okay, so now that we've built up all the different formulas, how to use it, etc., I'm just going to go through every single type of question that you could be asked so that when you do your homework or you do the exam, you should be so ready to tackle them. So the first one here, example 1, differentiate y is equal to e to the 6x minus e to the minus 2x. So we're going to be using the rule where we have a base of e and then you have a fancy power. So what you do is you're going to take the derivative of the power that comes to the front and then copy and paste. Then you do the same thing here, take the derivative of the power, which is negative 2. If you bring that to the front, notice how there's already a negative. So it becomes negative 2, and then you copy and paste. Okay, and then what happens is those two negatives become a positive, so you get 6e to the 6x plus 2e to the minus 2x. And that, notice how I kept my powers the same? Yeah, that is your answer. Choose a cuter color. Yay. Let's go to the next one. Example 2, differentiate y is equal to 2 over e to the 5x. So what you want to ask yourself first is, if I want to differentiate this using the above rules, it needs to be in the same form. This is not technically in the same form because it's not written as e to some power. It's written as 1 over e to some power or 2 over e to some power. So what you want to do is you want to bring the e up using your index laws. So we're going to get y dash equals to 2e. And then when you use your negative index laws, it just takes a negative of the power. Okay, great. Now this is actually, that's incorrect. There's not a dash there. It's still the original. Okay, and then now it is ready to be differentiated. So I bring the derivative of the power, negative 5, down to the front. We get negative 10, and then you copy and paste. Beautiful, nice and simple. Next, example 3, differentiate this, okay? At any point, please pause the video, have a go yourself, and then you can check and see if we got the same answer. I'm gonna notice here that we have a power that is x squared. So if I take the derivative of that, we're gonna get -5 times the derivative, which is 2x, and then you copy and paste just the e portion. So this is gonna give you -10x e to the x squared. Great, nice and quick. Next, example 4. What do you notice that is different? Yes, the base is not e, it is now 3. So try to remember, or you can flick back through your notes or the notes I have before. How do you deal with these ones? Well, the rule is that if you're in the form of a to the x, where a is not e, then its derivative is going to be copy and paste times ln of the base. Okay, so in that case, I'm going to copy and paste, and then I'm going to take ln of 3. That's it, guys. Next one, example 5. Differentiate y is equal to 5 to the power of 5x plus 3. So very similar to the previous one where the base isn't e, but what's more interesting is that the power is not just x, it's 5x plus 3. So we're going to be using the formula a to the power of f of x, and it's going to be equal to the derivative of the power, copy and paste, and then you take ln of the base. Okay, kind of sounds like I rhymed there. So now the derivative is going to be the derivative of the power, copy and paste, and then ln of the base. Wow. So now the last thing I'll do is I just want to combine the constants out to the front. We get 5 ln 5, and then I times it by the exponential. Yay! All right, next one. Differentiate y is equal to e to the 2x minus x to the power of 4. Okay, so you can see here, this is not just the e by itself. We have an e to the 2x, and then we have an x term, and then we have a power. You should hopefully notice that in order to differentiate this, we're going to have to use chain rule. So if I want to use chain rule, okay, you can tell it is going to be chain rule, hopefully, because we have an inner function, which is this guy over here, and then you have the outer function, this guy over here. That is when you know how to use chain rule. If you are still confused about chain rule, I really recommend you watch my other video. I've put it over here, Differentiation 101. I explain how to apply it and when to recognize when to use it. Okay, so what we're going to do is to use chain rule, you bring the power down, you reduce it by 1, and then you take the derivative of the inner function. So if I differentiate the inside here, we're going to get 2e to the 2x minus 1. And yes, you're going to have the derivative is like 2 terms. The only thing I like to do as a general trend is that when I write my final form using chain rule, I like to put it in ascending order. So constant out the front, and then when I say ascending, the thing that's smaller is the thing with the smaller power. So I'm going to write this second, and then I write the cubed one last. Beautiful. Next, example 7. Differentiate y is equal to xe to the 2x. Now let me show you what I have seen time and time again my students do, and it is wrong. Okay, you might be doing this as well, but I'll tell you now, wrong. So they will take the derivative of the x, which is 1, and then take the derivative of e to the 2x, that's 2e to the 2x. Okay, now why is that incorrect? Well, whenever you see two functions multiplying to each other. So the two functions that I'm referring to is when something has an x and another thing has an x. That's how you define it as being two separate functions. Then you're going to have to use product rule. Okay, remember product times. All right, so we're going to let the first function be u. So u is equal to x. V is going to be e to the 2x. And then I'm going to find u dash is 1 and v dash is 2e to the 2x. And then now we're going to go ahead and use product rule. So v u dash plus u v dash. And if I plug this in, v times u dash is here. So that's 1 times e to the 2x plus these two times over here, 2xe to the 2x. Okay, and then you can leave it like that, but I just love leaving it in the nicest form. So I'm going to notice that they both have a common factor of e to the 2x. So there's going to be e to the 2x, 1 plus 2x. And for me, that is nicer. So if you guys want a copy of the PDF, kind of like collecting a bunch of study notes for this particular topic, you can head to the link in my description box down below where you can access all these study notes. Okay, make sure you share them with all your friends. Sharing is caring, and that's how we go through this tough period of our lives together. Yay! Next, example 8, differentiate y is equal to e to the power of 2x plus 5 over 4x. Okay, so now you're going to notice we have two functions dividing, so it is going to be product rule. So, sorry, not product rule, quotient rule. So u at the top, v on the bottom. So u is going to be equal to e to the 2x plus 5. U dash is going to be the derivative of that, which is 2e to the 2x plus 5. V is going to be 4x and v dash is just going to be 4. Okay, fabulous. Now, let's see if you remember what quotient rule is. I beg you, please do not rely on the reference sheet. I know it's there, I know it's available, but the time that you spend flicking through your reference sheet, looking for the thing, in the exam, it's all gonna add up, okay? So you might as well get used to it during the term. All right, so the way that I memorize it, because I have all these tricks up my sleeve to allow my brain to memorize these things, is I write the v's on the outside, so vu minus uv, and then the v's on the outside are actually forming a larger V. I also remember that because it's quotient rule, it's a minus, divide, minus associated with each other, plus times associated with each other, and then u dash before v dash, alphabetical. Okay, perfect. So now if I plug this in, we're going to get 4 times 2e to the 2x plus 5 minus 4 times e to the 2x plus 5. Put this over here. And then we're dividing that all by 4x squared. So now to clean this up, we're going to expand it, simplify, everything like that. We're going to end up with 8x e to the 2x plus 5 minus 4e to the 2x plus 5. And that is all divided by 16x squared. Now you could leave it like that, but what I'm going to do is I'm going to factorize. I always do, because you might be able to simplify it further with what's in the denominator. So if you look at the numerator, what's common? Okay, you can see that a 4 is common. You can also see the e to the 2x plus 5 is common. So I'm going to factorize out 4e to the 2x plus 5. That is going to leave us with 2x in the first term and just a minus 1 in the second term. So then we end up with this. And then now I'll notice, yay, I can simplify further. There's a 4 left on the bottom. So we get y dash equals to e to the 2x plus 5, 2x minus 1 all over 4x squared. Hooray! And guys, that is it. I've gone through every single type of question that you could be asked, and hopefully you will be ready to tackle those problems. Thank you so much, and I'll see you in the next study session.